As you know from the, I don't know why this one doesn't work. As you know from the news, there was a sequence of earthquakes, the first of which was on the 24th of August with a magnitude of 6.2, centered with epicenter very close to the town of AMATRICE, which, as reported in the media, was in proportion destroyed, and indeed maximum intensity macroseismic scale of grade 10. Following that, there was a second series of events about 2 months later, the 26th and 30th of October. The second of these had a magnitude of 6.5, and the epicenter was some 50 kilometers northwest of the first one. Finally, in this year, around a month ago, less than a month ago, on the 18th of January, there was a third event of smaller magnitude, 5.5, just about 15 kilometers southeast of the first event. As you can see, the three epicenters are basically on a straight line, which identifies the fault that runs through the Monte Vettore, as we will hear later, and that is responsible for much of the seismicity of these areas. The events which are destructive magnitude, and it's for the Italian seismicity, especially the first one, was of particular shock for the public opinion because of the relatively high death toll, in fact very high death toll at 300, almost 300 people, with respect to having occurred in an area of very modest population density, around 15 people per kilometer square. Just to give an idea of the microseismic effect of these earthquakes, I'm reporting here some usability statistics, which are the ones that were collected within a month and a half of the first event by the Civil Protection, using what we call EDIS form, which are the national form for usability. We have different form for each of the private buildings, public buildings, and a cultural heritage. As you can see from the statistics, 2/3 of the schools basically were rated in class A, which means green tag, immediately usable. About 50% of the buildings were also, the private buildings were also immediately usable, but about 2/3 overall of the cultural heritage was indeed either collapsed or unusable. On the basis of this, we drafted some first preliminary mission objectives, which I don't go through because they will be clear from the presentation of my colleagues tonight, to which extent we want it. I just want to characterize a little bit more the event by first going through the historical seismicity, which here is presented in terms of the events over the last possibly more or less 1,000 years. In the 6 recorded, or which there is historic evidence, in the 6 towns that were majorly affected by this sequence of events. As you can see, they are clustered both in time, level of intensity, and locations, as is more evident perhaps from this summary image, where we are reporting the epicentral macroseismic intensity and the microseismic intensity at each of the locations, and you can see that there is some coincidence between the empty circle, which identifies the epicenters, and the dots, which identify the macroseismic intensity at each of the 6 locations. We also correlated this with events in L'Aquila, which, as you might have seen from the previous map, is only about 30 kilometers, let's say, east of the latest epicentral area. This is even more evident when we look, of course, at the shake maps, as the one produced by INCVI here, the Institute of National Geophysics and Volcanology in Italy, and the isoseismal P-ground acceleration distribution and acceleration at 0.3 seconds, which again show, in this case, very high values of acceleration. These are among the highest ever recorded on Italian territory, up to 0.7 G for the peak ground, up to 1.5 G for the maximum amplifications. The second event of the 30th of October indeed had smaller maximum accelerations, but had a much wider spreaded area, consistent, of course, with the greater magnitude, and also, as we will hear from Zoe, with the greater fault rupture and superficial evidence of this. This is quite clear from this comparison. But you can see that, for instance, the maximum peak ground acceleration at NORCIA was indeed the same value for the two events, although, of course, here the grading is different because the scale is different. In terms of further characterization of the strong motions, the Italian national network are some 350 accelerometers dispersed on the Italian territory, of which picked up the shaking. Of course, I'm not going to present you the results of all of this. You can access them at Ithaca MI INCVI IT, and these indeed are some of their results, some of their elaborations. I'm just presenting the records for AMATRICE and NORCIA here for the first earthquake, and you can see that the actual record, especially in the direction east-west, greatly overshoots the uniform hazard spectrum, even for the 2,475 years return period. This is not quite, it's more, oops, sorry, it went a bit ahead. Here instead we are simply comparing the two different events, and it's worth noticing that in the case of NORCIA, the second event had a very high level of amplification in the high range of period between 0.4 and 1.2, and this will be reflected, as we will see later, in some of the damage that we have seen in NORCIA in the cultural heritage buildings, and even more so when we consider the records that were taken by an instrument which was placed at some 150 meters from in the main square, very close to the two main cathedrals that collapsed, and which Paolo will present later. Just to complete the characterization of this second event, of which we will not speak at length later, I just would like to underline the fact that we also substantially high peak ground acceleration and amplification were recorded for the Z component, so for the vertical component of motion, in Castelluccio and in Accumuli, which are on the vertical projection of the fault plane. And as you can see, and indeed, such record is matched by the extreme level of destruction that both Castelluccio and Accumuli experienced in this second event. Here is the team. So it was about 15 of us that went to the site within over approximately 2 weeks in 3 different teams, so that we were able to move more in a more agile manner, and we made base in Rieti, where we were co-located with the Civil Protection main office that was taking care of this earthquake, and they were of incredible support to allow us to access, with the support, of course, of the fire brigades, the red zones of the 6 localities that we visited in details. Just without further ado, these are the contents of the rest of the talk. Zoe Mildon will present the geological aspect. Domenico Lombardi will present the geotechnical observation, and then the damage to urban settlement will be presented by Valentina Putrino. Davide Pedicone will talk us about the Italian codes and what are the provision for masonry building strengthening. Performance of critical infrastructure and cultural heritage will be covered by Paolo Perugini, and the performance of school and hospital by Flavia De Luca, and the social aspects by David Alexander. Notwithstanding the long list of Italian names, they are all resident in the UK. I just wanted to underline this. I will come back for some conclusion. So, please.
Thank you very much, Dina, for that introduction. So, as Dina said, I will be talking about the geology of the local area and what we could actually observe at the surface due to the earthquake. So this is a geological map of the region, and I've highlighted some of the main towns that we looked at. Most of the towns are situated on Miocene sandstones and clays, except for two towns, which is Pescara del Tronto, which is situated on some older and some younger sediments, and Retrosi, which is situated on much younger sediments from a lacustrine basin. So just to introduce, add to what Dina said about the sequence. So this is a map of the Central Apennines. Amatrice is there. And the Italian Apennines is a region of active continental extension. And this extension is taken up in a northeast-southwest direction. And this extension is taken up by a series of normal faults, which are shown on these red lines on this figure. So the last two major earthquakes in this region occurred in 1997, which is just to the north of the Amatrice sequence, 2009, just to the south, and then this, all the dots in green are aftershocks that have happened from the three main events. So, a normal fault is, this is a block diagram of a normal fault. So we have two sides to the fault. Usually the fault is orientated perpendicular to the extension direction. And when the earthquake occurs, one side goes up and one side goes down. And so we can observe these breaks in the surface, which is what I'm going to show you and what we've measured. So this is the area that we focused on. So this is the town of Amatrice down here. We focused along the southern part of the Monte Veteri fault. And this was also in collaboration with other researchers who had previously been to the areas. We covered this where there is the yellow lines, and this just shows you the number of data points we took. We took hundreds and hundreds of data points. So what were we actually measuring? This is what we see with myself for scale. So you can see this break, this crack in the ground. That is caused directly by the earthquake slip at depth coming to the surface. So this side has gone up and this side's gone down. So what we're measuring is we measure the size of this offset, the direction in which the offset occurred, and the orientation of the offset. This is just another photograph from a slightly different angle, so you can see how the two sides of this offset would join back to, or how the two sides separated. So this is just a quick summary of our measurements. So, the mean offset that we saw was about 15 centimetres, but there's quite a large range in that, from about 3 centimetres to 30 centimetres. And we saw some other variations in the orientation and the opening direction as well. These are just some other photographs to show you. So this is a small boulder that was along the rupture and along the crack. And as you can see, the energy during the earthquake was high enough that this rock cracked straight across it. And so you can see really clearly the direction in which these two sides, separated. Here's just another picture of it through a rupture through the soil. And then this is this is a limestone fault plane, so this has been formed over many, many earthquake cycles. But if you look right down the bottom here, we zoom in, there's a change in colour from this grey, darker grey weathered rock to pale white rock underneath. That white section is what was exposed during the earthquake, so we can see really clearly what the height of this was. So why do we care about doing this? It's important to look at the geometry of faults because the hypothesis is that the geometry and the strain across the faults and the stress across the faults are interrelated, which then will affect the seismic hazard of the fault. So that's why we're making these measurements. So remember I said that the maximum slip we observed during the EEFIT mission was 30 centimetres. For contrast, these are some field photographs from after the 30th of October rupture. I was in the field 2 days after this occurred with some colleagues. This was the maximum that we observed, which was nearly 2.5 metres compared to 30 centimetres. At this location, we can actually see the two different earthquakes. So you see this grey rock here was what was already exposed. That little pale white stripe there, which is about 10 centimetres high, was from the 24th of August, which killed 300 people. And this section down the bottom here, this slightly brown section, which was about just over half a metre, was from the 30th of October. So you can really see what the difference is of the different magnitude events. So that's my section over, so I'm now going to pass over to Domenico, who will continue talking about the geotechnical observations.
Thank you, Zoe. Thank you. I am Domenico Lombardi from University of Manchester. So I will describe the geotechnical observations made during the EEFIT mission. So in total we surveyed an area of about 490 kilometers squared, stretching from 5 kilometers south of AMATRICE, going north through Accumuli and to ARQUATA del Tronto. You can see also the epicenter, which is located very close to Accumuli. This is the epicenter of the first main event. The main goals were to locate and characterize the secondary seismic effects. By secondary seismic effects, I mean the effects directly related to the ground shaking. We used these observations in order to determine the earthquake intensity through the environmental seismic intensity scale. Regarding the different share of the observations, which you can see here in this plot, we observed mainly rockfall, especially in the region around ARQUATA del Tronto because of the topography of the area. We also observed a number of landslide, retaining wall failures, ground cracks, and some hydrological events. Before describing the geotechnical observations, let me introduce the environmental seismic intensity scale. So we are going to use this scale in order to estimate the macroseismic intensity. This is not complementary to the Mercalli scale. It's rather complementary to the conventional modified Mercalli scale. Similarly to the Mercalli scale, we have 12 degrees, and usually this scale increases in accuracy when we are looking at intensity higher than 8 degrees. Now, the scale is based on both primary effects, which are directly related to the fault rupture, like surface rupture and tectonic subsidence and uplift, and also secondary effects, such as ground cracks, slope movements, liquefaction processes, which were not observed in this earthquake, and also anomalous waves or tsunamis, which were also not observed in this earthquake. Also, depending on the area affected, we observed that the higher is the area affected, the higher is the intensity scale. Now, in the subsequent slides, I will focus on slope movements. You can see that depending on the volume of the material displaced, we can associate different intensity levels. So let me start with the town of Pescara del Tronto. So this is Pescara del Tronto. This is Via Salaria, which is one of the most important road connecting Rome to the Adriatic coast. This photograph is taken before the first main event. This is the photograph immediately taken after the 24th August earthquake. You can see the extent of damage was very evident. In particular, we observed a number of landslides located in different areas of PESCARA del Tronto, but we are going to focus on two main landslides. One landslide occurring very close to the quarry. So these are photographs taken during the mission. You can see that the slope had an initial height of about 6 meters. The type of movement can be classified as a translational slide. You can see another photograph of the slide in this figure. Also, it is worth noting that we could observe a pipeline on the face of the slide. The amount of material displaced was about 2,500 meter cubed, which corresponds to an intensity level of 8 according to the environmental seismic intensity scale. Then we are going to focus on a different location again in PESCARA del Tronto. This slope was facing directly over the Salaria Road, and you can see on the bottom left a photograph taken before the landslide. You can see that the slope was quite steep and vegetated, and the two photographs above were taken during the mission. So they show also the extent of damage. Also in this case, the type of movement can be classified as a translational slide. The volume of material displaced was slightly larger than the previous case. It was about 3,500 meter cubed, which again corresponded to an intensity level of 8. Then let's move on to AMATRICE. So this is AMATRICE before the earthquake. This is after the earthquake. You can see the extent of the damage to the built environment, but in this presentation I'm going to focus on the geotechnical aspect. In particular, I'm going to focus on this landslide, which occurred on the northwest point of AMATRICE. You can see on the top left a photograph taken before the earthquake. You can see there is a retaining wall, again a very steep slope, and these other photographs were taken after the earthquake during the mission. You can see again the type of movement is a translational slide, very steep, which affected also the road below the slide, and this road was closed for a number of weeks. The quantity of material displaced was significantly larger. It was of the order of 10,000 meter cubed, which corresponded to an intensity level of 9 according to the environmental seismic intensity scale. Now, let me also touch upon the topographical effects. Now, topographical effects are very important because the ground motion can be significantly amplified by topographic irregularities. And in the concentration of damage in ARQUATA, which is located on the crest of this relatively high and steep ridge, suggested that topographic amplification may have played a major role in the high concentration of damage. Now, if you consider the geometry and the topographical features of this locality, you can see that it is relatively high, and the base of the ridge is significantly larger than the crest. And according to Eurocode 8, this is this type of topography falls in category 4, for which the code recommends an amplification factor of 40% for the peak ground acceleration. We also surveyed a number of dams. In particular, I'm going to focus on the CAMPOTOSTO artificial reservoir. CAMPOTOSTO, it's worth mentioning, is one of the largest artificial reservoirs in Italy. It is impounded by 3 dams, one earth dam located on the northwest in Poggio Cancelli, and 2 concrete dams, one in Rio Fucino and one in Sella di Pedicate. We didn't observe any significant damage to the dams. Also, we are not aware of damages caused by subsequent events. However, there are major concerns because of the presence of this active fault, which is crossing the concrete dam in Rio Fucino. I will now hand over to Valentina.
Thank you very much, Domenico. So, good evening, everyone. I'm going to talk about the structural aspects investigated by the team on site, and in particular, I will be focused on damage to urban settlements. The 3 main investigation methods we used on site were rapid visual survey form, omnidirectional cameras, and the web-based knowledge expert tool called LogIdea. Rapid visual survey form have been extensively used in other EEFIT missions. And in our case, we tailored our form to accommodate the information needed for the Italian building stock, both masonry and concrete structures. It takes no more than 10 minutes to be filled and is made of no more than 30 entries and is divided into 3 main sections, which are localization, structural information and tagging, and damage observation based on the European microseismic damage scale. To give you a sense of the damage that we collected on site, this is a picture that shows damage grade 1, so negligible to slight damage, damage grade 2, damage grade 3, substantial to heavy damage, damage grade 4, very heavy damage, and finally collapse. 360 camera came to help when the time to be spent on site was very limited, especially in red zones such as AMATRICE. In this case, as you can see, if collected in sequence, 360 images can be then uploaded on platforms such as Mapillary and then reused to review collected data or eventually integrate missing data. It has been used for the first time during the 2011 7.2 Van earthquake in Turkey, and it has extensively been improved since then, and it was also used during the last EEFIT mission in Ecuador. And finally, LogIdea, which is the web-based knowledge expert system for damage collection and failure mode identification based on trees for identification of damage due to earthquakes for architectural heritage. It has been developed by Novelli and Ayala within the Perpetuate project, and it has been extensively used during other case studies such as L'Aquila, Algeria, and Slovenia, Ljubljana. It is an open source and is readily available online. So what were the limitations we encountered when we were on site? First of all, the very limited time to be spent within red zones, the very limited access to building, and the very widespread level of damage. In terms of rapid visual survey results, we plotted our results based on the tagging classification and the EMS 98 damage scale. And what we understood was that the level of damage that we recorded was quite widespread, as well as quite different among the cities we have been the chance to visit when we were on site. Especially if we look at the case of Arquata del Tronto Bassa, more than 60% of the buildings were rated as safe buildings, and only 40% of the building as restricted use. Few meters far from Arquata del Tronto Bassa, in Arquata del Tronto Alta, more than 80% of the building were rated as restricted use, with only few cases of safe building and completely collapsed building. The major number of buildings that were rated as unsafe was in Amatrice and Pescara del Tronto. In relation to the damage that we collected on site, and according to the European microseismic scale, we were also able to give an intensity degree to each one of the cities we visited. For instance, in the case of Amatrice, the level of damage was graded 10. And as well as Pescara del Tronto. In the case of Arquata del Tronto Alta and Accumoli, the intensity grade was 8, and in the case of Arquata del Tronto Bassa in Castelluccio, the damage grade was 7. We then mapped our results to see the extent of improvement going from the damage we collected through rapid visual survey, and the one we collected we were able to improve by using 360 images. And we then compare it with the available online satellite images, so the satellite images provided by Copernicus, which is a service that activates in the aftermath of any hazardous event, providing information, aerial views of the damaged area. And in the case of Amatrice, where the extent of damage was quite widespread, the two layers of map were corresponding quite well as Pescara del Tronto where the two layers of map were able to correspond quite well. And the difference stays in accumuli, where, of course, the extent of damage was far less compared to the previous events, to the previous cities. And it was, as it is possible to see from the overlap of the two maps, the extent of mismatching is quite important. The same in Arquata del Tronto. And in this case, we pointed out a case of this building, which is the City Hall building located in Arquata del Tronto Alta, which, based on the Copernicus map, it wasn't even marked as potentially damaged, while when we were on site, we were able to see the real extent of the damage of this building, which we analyzed using log idea, which is based on the geometry of the building itself, the layout of openings, the position of the cracks, was able to give us the most probable collapse mechanism for this particular case, which is actually the in-plane failure of piers and spandrels characterized by X-shaped cracks, which we were able to see on site. So that's all for me, and I leave the stage to Davide.
So, good evening. I'm now going to talk about the MASONRY buildings, and in particular about residential buildings. And so far we have analyzed all the extent of damages and the observations at territorial scale, and now we are going to focus on the residential buildings, and then there will be a section on bridges and churches. In this first slide, we would like to understand the development of the Italian seismic code during the years in the 20th century. So basically, after the Messina earthquake, there's been a big push in terms of research and codes being deployed in Italy. And for example, in 1926, two seismic zones have been defined, but it's only in 1984 that AMATRICE has been classified as seismic for the first time, and it has been classified as seismic zone 2. And then in 1998, AMATRICE was classified as seismic zone 1. This is quite relevant because, as we can see from these pictures, where we see AMATRICE in 1951 and AMATRICE in 2011, all the buildings in AMATRICE and the surrounding area basically were mainly built during the first half of the 20th century. And therefore, these buildings in general have not been designed and constructed with any seismic provision. And in general, there was no duty of a compulsory retrofitting and strengthening for these buildings unless many changes were to be applied to the building, such, for example, a building extension. So, in terms of the code requirements from the Italian Seismic Code, we have analyzed both the currently applicable NTC08 and also the codes that were in use during the 80s. And the idea here is to provide with a benchmark of what an ideal masonry building should look like, and then to assess the observations and the damages against this benchmark. So in terms of structural concept, of course, there is a recommendation for regularity. So the building should be as much as possible symmetrical in plan and regular in elevation. This is not compulsory, but it's highlighted and recommended by the code. In terms of the maximum number of floors, AMATRICE is nowadays considered as seismic zone 1. So the maximum number of floors that you will be able to build in terms of a masonry structure would be 2. until 1986. And today, because the code is obviously a performance-based code, you are allowed to design a building with more stories, but this provides with an idea of the fact that masonry buildings in general should not be constructed with more than 2 stories, according to the Italian code. In terms of requirements for the materials, it is important to notice that brickwork with artificial squared blocks in concrete or hollow pots are allowed. Squared natural stone is allowed, but unfortunately in Amatrice rubble masonry is not permitted, and by the way, it was not permitted to have buildings more than 2 stories even during the 80s, in the M86. So, as we have said, Amatrice only became seismic in 1984, so all the prescriptions that we have seen so far were not really applicable in Amatrice before 1984, and therefore it is worth understanding what strengthening measures for existing buildings were prescribed in the DM86. So obviously there are 2 strategies. The first one is the reduction of masses, which in honesty we have not seen on site. And the second one is the strengthening of the structures and the walls. So obviously there are many possible approaches. The first one was to build concrete ring beams at roof level in order to tie all the masonry walls together and enhance the box behavior of the structure. A second one would be to encase the concrete, to provide a concrete encasement to the masonry walls in order to improve the confinement of the walls, and this would obviously be beneficial, especially in case of cavity walls. And then again, the mortar injection to enhance the mechanical characteristics of the walls, or the steel rods that would prevent the walls from falling out of their plane. Now, this provides, again, a basic benchmark for the ideal buildings or the technologies that were in place to strengthen an existing building. What we have observed on site during our mission is slightly different from what you would expect for a new building in Amatrice today. And this can help explaining the reason for such a level of devastation. In terms of number of floors, both in Amatrice and Accumuli and Arquata del Tronto and Pescara del Tronto, we have seen buildings up to 3 and 4 story, so 15 to 16 meters. Many 2-story buildings, but unfortunately many 3 to 4 story buildings, and this is a major key driver to explain all the damages that have occurred. Then in terms of quality of the materials, we have seen very poor quality of the materials, especially in terms of mortar and use of natural stonework with non-squared rubble masonry. So this is also very relevant to explain the extent of damaging. As you can see from these pictures, the mortar was absolutely ineffective, and all these buildings have collapsed as a result. In terms of damage observation, we have seen a number of different damages. In all those cases where the buildings could behave as a box, so it has behaved slightly better than others. Although we have seen so many cracks, at least the building is still standing. While in other cases where we have seen out-of-plane failure of the masonry walls, obviously in in many cases, this has caused casualties and the full collapse of the building, as you can see in these pictures. So, to summarize, in terms of the existing building, it's possible to say that the bad quality of the materials and the fact that the buildings were too high somehow can be described as the two main reasons for this level of devastation. Now, in terms of strengthening of the existing buildings, we have described the various methodologies. What we have seen on site is that basically there has been a shift between the technologies that were used in the 70s and the 80s, and then after the 1997 Umbria and Marche earthquake, a different set of technologies have been used. In the 70s and 80s, basically there was a big degree of confidence about concrete, and therefore many concrete encasement and ring beams. But unfortunately, for example, in this case, the use of ring beams has been done in a non-appropriate way, and in fact, a concrete ring beam has become a concrete roof, and this was quite a usual type of situation on site. So many buildings have collapsed because the ring beam and a concrete roof has replaced the existing timber roof, and this is one of the results, for example. So these two approaches, the concrete encasement and the concrete roofs, have proven not efficient and counterproductive somehow. While on the other side, mortar injection and steel ties have proven slightly more performant, and for example, mortar injection, here we can see two pictures. The second one at the bottom, we can see that the building is almost undamaged, and it is adjacent to another building that has collapsed in ARQUATA del Tronto, and the first one in AMATRICE. There are obviously cracks and damages, but again, the building is still standing. In some cases, especially when the steel rods have not been used together with the mortar injection, the results have not been necessarily positive. For example, the picture on the left, we can see that the steel rods is overstressed and the building has collapsed. On the right, we can see that there is an incipient out-of-plane failure of the facade. But in general, for example, in the picture on the left, this three-story building in PESCARA del Tronto has suffered almost no damages apart from the corner, as you can see, and it has the mortar reinstated and also the steel rods, while in the one on the right, again, we have many damages. The steel rods, unfortunately, have only been applied at roof level and not at first floor level, and so we see the out-of-plane rotation of the facade, and the corner, unfortunately, has failed completely. So now I'm going to hand it over to Paolo.
Thank you. Thanks, Davide. So we'll start with the critical infrastructures, particularly with bridges, and apologize in advance, we are running out of time, so I'll be flying through some of the slides. This is a map of the area you'll be familiar with, and each single red point shows one of the bridges, one of the structures we had surveyed. We won't see them all tonight, unfortunately, but this is just to give a flavor of the type of structures we observed. We see masonry bridges, which are the ones that suffer the most, and a range of concrete bridges, particularly concrete viaducts on highway structures. We will focus around this town of Amatrice, where we observed a range of bridges in the surrounding, and each road leading into Amatrice as a bridge has been affected by the earthquake, and this caused lots of issues in terms of providing access to the emergency services straight after the event, and it was quite bad. It made also national news. We will focus on this particular bridge. It's called the Three Occhi Bridge. Three Occhi means three eyes. You can see these are three arched span structures. And this is along the road leading to Amatrice from the south. And this bridge is now unusable. It still is unusable, and it caused lots of issues. As much so that the army had to step in and build a road bypassing this bridge, including the new temporary bridge that you can see on the top left corner. And this was completed just after a week after the event. This shows how important some infrastructures can be for the rescue and emergency services. This is a plan of the bridge in which I marked up the main damage. The main one being a very large sag by the eastern abutment. We're talking about a sag in the order of 200 millimeters. And this sag originates because of the extensive damage on that abutment. We'll see more of this later. And we also observed a range of other damage, both to the piers, to the arches, as well as to the western abutment. This is a picture of the eastern abutment looking from north. You can see there is a geotechnical failure, what is effectively a retaining wall, in which lots of material has been lost, and that created part of the sag. You also notice these three vertical buttresses. These are reinforced concrete buttresses which are completely failed, both in shear as well as in overturning. I think the buttresses there are quite interesting because they're obviously not original to the bridge design, but they've been added at some point during the lifetime of the structure. And that is possibly due to the uneven load condition. You can see the ground level is different. There's approximately a 5-meter difference between both sides of the abutments. But this tells us that someone recognized there was an issue, a geotechnical issue it tried to do something about it, but obviously that was not that successful. And the seismic acceleration created the failure of the abutment. You can see the damage we observed on the first vault just by that abutment is also highlighted by the cracks, and the crack patterns is also compatible with the movement of the abutment itself. Now, looking at concrete bridges, particularly concrete viaducts, we looked really hard for damage. We were really keen to find some damage. Unfortunately, we didn't find much. No, actually, fortunately, we didn't find much. And that is quite extraordinary, especially because most of the structure were not designed for any seismic action. They didn't have any seismic detail, any seismic restraint system. This is pretty much all the damage we found. There is a diaphragm on top of that pier that suffered some pounding. That shear key there suffered some cracking. And there's evidence that some of the road surfaces are cracked by the expansion joints. They've been repatched after the earthquake. We now move on the performance of churches, particularly a number of churches surrounding the city of NORCIA. In green, you'll see the churches that we surveyed, and it's worth noting that we were there on the 9th of October. We obviously observed the damage after the 24th of August earthquake, but the situation on the field changed substantially since we've been there. We have pictures, and I did a follow-up visit in December, and so we will be able to see the evolution of the damage in certain cases. Most of the churches were closed, all of the churches were closed when we were there, and that's as a result of the usability surveys. This is just the form that is used. It's worth noting that the form is based on what you see on the pictures on the right-hand side, which is a catalogue of collapse mechanisms. These are a number of damage that have been observed throughout the many earthquakes that have been in Italy, unfortunately. And it is recognized that churches being a certain building typology with a certain element types with a broadly known proportion suffer certain damage. And we'll see some of these later on in some churches. We will see some of them. I'm going to move from north to south. I'll start with the San Tizio Abbey, which is quite a kind of a spectacular abbey complex which dates back to the 5th century. We focus on the main building, which is in the middle of the complex. Is the church. Is a simple single nave church with a timber truss roof. And this is the chancel arch just above the altar, and there is clear evidence of a 3-hinge mechanism there. In fact, we can observe cracks at the springer, at the arch crown, as well as the other springer, where there's evidence that the tie has been quite successful at restraining this arch. in fact, we can see evidence of pull-out there. And this is how that form that I showed you earlier identifies this particular damage. In the same church, what we've seen is evidence of cracks just on the front facade, with some heavy cracks going from the purlins down to the rose window. And again, this type of mechanism is identified in the form. This is quite interesting because we were there on the 9th of October. That's the picture we've taken on the far left. We obviously observed the cracks. After the 26th of October, that mechanism evolved and led to the partial failure of a portion of the facade. And after the 30th of October, there's much more widespread damage. Although this is possibly due to the fact that pretty much the rock cliff with the entire bell tower that was above it came on top of the church. So very, very extensive damage here. We move on the next church, which is the Church of Sant'Andrea in the small town or village of Campi. This church dates back to the 14th century and is being modified, repatched after many, many earthquakes. The church roof was remade after 1979, and the porch you see at the front was brand new, made after the 1997 earthquake. Here we identify a variety of damage, but the main damage we identified was the overturning of the facade, as highlighted by a vertical crack between the facade and the other side walls. That could also be observed from the inside. You can see the facade detached from the vaulted ceilings. And then came the 26th of October earthquake. You can see how that mechanism evolved. Now the cracking is much more severe. The porch obviously had retained the facade to some extent, although it suffered very, very high displacement itself. And after the 30th of October, this is a picture taken in December, the entire facade with the entrance porch completely collapsed. So again, another instance in which we can see the collapse mechanism and then the progression of that mechanism with the earthquakes. Finally, we go down to the city of NORCIA. You might have seen some of these churches on BBC because they made the national news and international news as well. We start the so-called CO-CATHEDRAL of Santa Maria, which is just on the main square, on the main piazza of NORCIA. It's a very large church with a main nave and two side aisles. This church also had, a roof that was made after 1979. The church was damaged after them. And in here we observed a portal frame type of mechanism in which we observed the church behaving as an entire structure on the east-west direction, transferred to the church main direction. In particular, we could observe horizontal cracks on the side walls on both sides, longitudinal cracks on the vault's crown, as well as horizontal cracks at the central piers on both sides of the piers, highlighting the cyclical nature of the movements. And the east-west direction is the main direction of shaking, as Dina highlighted earlier. And this is how the mechanism is identified in those catalogue. Another mechanism we observed was a possible overturning of portion of the facade, in particular of the facade gable. And we can see here, after the 30th of October, how that mechanism eventually led to the partial failure of the facade. Now, a rough estimate of the first mode of vibration on the facade as a standalone cantilever is in the order of 1 second, which is in the region of the high acceleration, as Dina pointed out earlier. Moving on onto the next church, this is just adjacent to the previous one, is the main cathedral, is the San Benedetto Cathedral. You might have seen videos of this church with people evacuating it. When we were there, we observed a widespread damage, in particular on the side walls. We also observed evidence of the damage similar to the Santa Tizio Abbey, just between the purlins and the rose window. But we couldn't quite identify any evident mechanism in this church. What happened after the 30th of October is obviously almost complete destruction of the church itself. And evidence is that the bell tower on the right-hand side collapsed onto the church building. In fact, if you observe this picture, which was taken just after the earthquake, you will see no debris on the road coming from the bell tower. Also, the plane of failure, the diagonal plane of failure of the bell tower is compatible with the tower overturning onto the building. And also the walls on the sides towards the bell tower suffer much more destruction than the bell tower itself, than the walls on the other side. And also quite spectacularly, the facade is still there standing as a standalone cantilevers, whereas the rest of the building behind it is completely demolished. Interesting to know accounting for the geometry of this facade, the period is a bit longer, it's in the order of 1.5 seconds, in which there's a much greater reduction of acceleration in the spectra recorded. And when I was there on the 23rd of December, there was a temporary shoring which was placed in that church. I'm now just going to conclude with a short video that shows the relationship between the two churches. This is the first that we already observed. You can see the roof has already collapsed. It's completely collapsed. And then we look at the other church, in which we can see the remaining facade still standing. And this is evidence of the bell tower that has then collapsed onto the building itself. I now leave you to Flavia, who is going to talk about performance of RC buildings.
Thanks. Okay, so I will go through very quickly the performance of RC building and some other critical structure. In particular, we will look at the performance of schools. On RC buildings, we used the survey made through the rapid survey forms that Valentina already showed, and we collected a small database of 42 buildings in the city we visited. Most of the data are in AMATRICE, ARQUATA, and some data in Accumuli and NORCIA. Why? Actually, the database is very small, also because the distribution of construction typology in the area is mainly masonry. Actually, I represented here some of the data from the last census data from 2011. The scope and the use we are currently doing of this data is a one-to-one comparison with the analytical approach, and in particular, analytical approach calibrated on the data we collected for L'Aquila earthquake. So, you know, they are two earthquakes in a similar area, and it's nice and interesting to see if the material calibrated, the data and analytical tool calibrated for L'Aquila can be used or reused to interpret the damage for this area in central Italy. Now, this is just a view of the macroseismic intensity map with the critical building we visited, in particular hospital and schools. This is the macroseismic intensity, and this is the peak ground acceleration. In this case, the data are from the USGS. Now, just one note about schools, because we call them in critical structure, and they are a critical aspect all over the world, but in Italy, the collapse of a school has been also a turning point for our building regulation. After the 2002 Molise earthquake, after the death toll of 27 children because of the collapse of school, we had what I like to call the Copernican revolution in terms of both seismic classification and seismic provision in Italy. And as Davide has shown, actually the area that we have visited is classified as red zone. Since that, a lot has been done, and many programs has been made in Italy on the safety of school. One thing that I want to point is the fact that actually the Ministry of Education has a web portal in which not only you can look for all the school and look at the performances from you know, information about the school in general, but also information about the building in which the school is realized. The only problem, because I was going through this database to find more information about some of the schools we investigated, the point is that this database at the moment is not fully populated. So the thing is that a lot has been done so far, but for sure is not enough, as I will show you in through some of the damage we have seen. The first school I'm presenting is the school Capranica. Actually, this was a building that was made of three different units. It has a masonry part and two RC part. The reason why this building, I would say, is one of the mostly discussed right after the earthquake is that after the 1997 there were some intervention and some retrofitting action done on this building. The results after the August earthquake is what you can see. And actually the masonry part of the building completely collapsed. The thing is that the kind of intervention that were done to the school were mostly related to the RC part, in which you can see some FRP application to the columns. The thing is that the funds to retrofit the school were not enough, or actually the amount of fund for this school were not enough to make a full retrofitting. And this is just to show, this school suffered a very significant damage. What I'm going to now I'm going to show you some other school very quickly that are the Accumuli School. That was an RC building with masonry field, in which the damage we classified was limited to medium, and then we have NORCIA. The case of NORCIA, when we visited it, in NORCIA we visited two schools that are right outside the city center. I pointed also the San Benedetto church that Paolo showed to you. Actually, when we visited NORCIA, the level of damage was very limited, and the two schools we have visited, in particular the Istituto Tecnico Commerciale, was fully functional. This building is an RC building, and this is, now I'm going to show you a situation in which the retrofitting done right after the 1997 earthquake was quite successful. In this case, steel bracing were applied to the first floor, and in terms of damage, what we observed were just very limited crack. This is a picture I took from the news of the same building right after the 30th of October earthquake, but still you can see that even if there is some damage, more significant damage to the plaster, still there are no structural damage at all. This is another building that was another school that was a masonry building, not in use at the time, was not considered not usable, and we pointed some of the damage observed for the school. The other two schools that I'm going to show you are in ARQUATA, where you can see, as Domenico pointed, there was a very high amplification. The PGA, according to the USGS map, is 0.64 G, and we can see the picture of the school from Bing Map and the Google Street View before the event, and this is the level of the damage of the school right after, when we visited it in the second week of October. You can see that in this case the damage is quite widespread. This is another school, an RC building, and in this case the damage was very limited. The only situation, the only failure, I would say significant failure, structural failure that we found for this building was this incipient shear crack in the column, but most of the damage were, I would say, no structural. I collected also some of the data on the Grifoni Hospital, one of the two hospitals we visited, and where there was also the evidence of some concrete spalling, and we made some preliminary comparison. What I'm going to show you is just a simple proof of concept about the fact that some of the fragility curves calibrated based on Central Italy data, so on L'Aquila data, given the PGA registered for this event, what would be the damage predicted and what was the damage observed. These are the two different calibrations. The first one is just for regular building, and you can see that the DS1 for 032G of the NORCIA Istituto Commerciale could have been predicted and fairly, from an analytical point of view, would have been the result of an analytical analysis. The situation is different for the case of accumuli, which you can see that the fragility calibrated for regular building would have predicted DS1. This is a nice example because the school in accumuli was built on a slope. So to some extent, this kind of additional vulnerability can be the cause of the mismatch of the prediction. And in the case of the school in ARQUATA, actually the DS3 predicted could have been predicted also analytically through the fragility curves calibrated for the L'Aquila case. I will pass to Professor David Alexander. Thank you.
Thank you. Good evening, and it's a pleasure to talk to you in this, which we believe is the centenary year of the academic discipline of disaster studies, but we will be doing more to justify that statement later in the year. In the meantime, our job here was to look at two elements. Firstly, the plight of the population, and secondly, the role of the emergency services. I concentrate upon the latter because the former, the plight of the population, was not altogether easy to study systematically. Many people have been transferred from the affected area to the coast, for example, San Benedetto del Tronto, which is quite a considerable distance away from the affected area. Nevertheless, it was possible to make some observations, and we were interested, given the depth of studies in the past and so on, to reevaluate some of the original theories. For example, is there such a thing as a therapeutic social system, as Charlie Fritz and Alan Barton have suggested in their work a considerable time ago? Is there indeed a therapeutic community? And how does that match up when we have a renewed interest in the culture of disasters, and we're here in a mountain culture where there is a fairly high degree of personal self-reliance, in other words, of personal resilience, but a fairly low degree of communal solidarity, shall we say. So our conclusions on that were that the therapeutic community of the early stages of disaster probably does exist, but under rather difficult circumstances, characterized by fear, uncertainty, frustration at the situation, grief, sadness, and a degree of disorientation. We have to remember also that proportionally the earthquake created very high levels of destruction and displacement, levels indeed that I haven't seen in Italy since 1980. And that added to the situation and caused very considerable displacement of people, although according to a plan that was well developed and well articulated, where they would be moved from tents into temporary accommodation in hotels or with relatives, and finally into transitional housing, which was being planned at the time we were there in early October, and they hope to have ready between about now and the end of the spring. But in the meantime, there were many difficult personal problems and processes coming to terms with bereavement, for example, and very high levels of destruction that brought us back to recall, for example, certain key incidences in the earthquake that occurred in 2009. For example, the death in L'Aquila of Ilaria Placentino and her very young son, which was one event that significantly moved the population there. This brought us also to ask whether the work of Anthony Wallace a long time ago should not be re-evaluated, in that he discerned a disaster syndrome, and elements of that were definitely there in the population at Amatrice, and hence I think this deserves re-evaluation, particularly in the light of cultural differences there. What did people do? Well, one aspect that did betoken a little social solidarity was that young people in ARQUATA del Toronto set up a Facebook site to provide information to the population. I'd like to say a few words about information very briefly. But they were fulfilling a role that the authorities really had not fulfilled adequately, and they were very proud of the fact that they were also interviewed by the BBC. And no fewer than 7,500 people became friends of this Facebook site, which provided official information wherever it could when the authorities were not doing that. Turning to the situation of the rescue forces and so on, the rescuers were more numerous than the population. There were probably only about 4,000 people in the 4 towns affected by the August earthquake, but the rescuers numbered a total of 7,500, a situation that was also true of the L'Aquila earthquake, although it certainly won't be true of the next magnitude 7 earthquake to occur in Italy, when a very much larger population will be affected. Well, what about information, or what about problems? Well, reaching the affected areas was decidedly the most important problem in our survey of the responder community in the early phase. Other problems were much less significant, and this reflects the fact that the bridges were damaged and there were great difficulties of merely getting there and getting equipment in. In terms of information in the early phase, that was dominated by requests for information on people's safety and on temporary shelters. And how was information got over? Well, face-to-face communication dominated over all others. Despite the immense potential of social media, it simply barely figured, especially in official communication. What did people want to know about at the later stage? We were there about 6 weeks after the initial event. Psychosocial support and temporary shelters dominated the demand for information, but once again, face-to-face communication still prevailed, and the situation had not particularly changed. So I think we could say that the official sources of information were firstly not giving out information very systematically, and secondly not using modern means that the population had considerable access to. We also asked about awareness of long-term issues, not among the population this time. Their awareness was very low. Planning was going on, and it's quite good planning, but there does seem to be something in Italian culture that, although the planning may be good, the communication of it very often isn't. But we asked the rescuers and the emergency forces what their awareness of the reconstruction and longer-term issues were. Generally, they had a good awareness regarding their own organisations, but there was little in the way of a common operating picture, in other words, sharing information between organisations about what was going to happen next.